looks like the lapel is flat, so I can't use that. I'll have to stand still, but see how we go, see how successful I am. All right, so I'm Dr. Renee Gorham. I'm teaching the next 4 weeks. What happens usually is David Ponting and I coordinate the PHYS1210, so I do it in semester 1, he does it in semester 2, but that means you basically have 2 coordinators. So if you have any other questions that you can't bother emailing David and you see me, you can ask me as well. But I'm only teaching the next 4 weeks of mechanics. And then you have Lachlan, who will teach them more physics, and I'll sort of touch a little bit on that during my time for the 4 weeks. And then David will come back later on. So I just wanted to just send some reminders. So just reminding you all that we have the weekly quizzes. Now those quizzes are worth a total of 10%, I believe. I can't remember now. I should say I have had a cold and I've been tested many times. So I'll put my mask on at the end when you come talk to me, but I won't during the lecture. So weekly quizzes, you can do them as many times as you like. The reason why we've got instructions that say it, but last semester people forgot. So you can do them as many times as you like. It's like a homework exercise. So you can do them. There's a whole bucket load of questions there that you can have access to. So it's really good to know that you can have many goes. We've got my lecture notes, which we'll go through. And then we've got the laboratory. So I'll do tomorrow morning's laboratory. I wasn't there last week, but I will. Is that mine or someone else's? No, that's all right. I was like, oh, sure, I'll put it on silent. Okay, so yeah, and we've got the tutorial, and the tutorial answers will come out later this week. So we've got my lecture slides. Oh, and I've got no internet. Okay, I'll just check before. Let's try again. I haven't taught in this lecture theatre. I've only done a presentation here. It doesn't want to give me access to internet. Sounds about right. Let's try again. There we go. All right. So we've got my lecture notes here. And so what I've done, because we have had such a sort of online, offline transition over the last 2 years, is that there's lots of content online as well. So if you do have to stay at home, hopefully there's enough here to keep you motivated and up to date. So I've got all the learning outcomes for each of my lectures each week. And I've got the lectures, videos. You'll have the updated ones from this year's semester as well. They'll be available on Panopto, but I just put these here in case someone wanted earlier access. And then, of course, we have the lecture slides that I present and the checklist for the week. Now, if you click on one of these, it will take you to another page, and it's going to summarise everything that I go over. So there will be embedded videos here that I use in lectures, and then also a little bit of context. So it's a little bit of a narrative behind what we're teaching you, because sometimes the slides can be a little bit minimalist. So that's what we've got. You've got everything here that I'm teaching, and what I'm trying to do, but it takes time, is have the worked solutions there as well. So I go through examples and I'll write them here in front of you, but if you can't make it to the lectures, you can just have a look there so you don't have to search in the lecture. So yeah, that's what we're going to cover today, a little bit of vectors, and then we've got a quiz at the end. So I'll get you to access that if you can at the end of this lecture, and you can have a little test your knowledge. Not worth anything, but it's just a little bit of a summary of a multiple choice question summary that you can access. And if you have any problems, you can come see me during that time. So it'll probably be the last 5 minutes of the lecture. And you can do that here, come down and ask me questions, and we can go. All right, so I'll leave that up. I forgot. Yes, I was talking to David. There is a class test next week. So that's going to be based on David's content on cosmology and particle physics. And then this week's mechanics section. So it's going to be a really easy subject for my area. I haven't written the question yet, but I'm sure it'll be great. So it's going to be on either SI units, vectors, or kinematics. So we'll go through that. So that's next Friday. Any questions? A little bit of a spew there of information. So what we're going to go through today is a very back to basics lecture. So hopefully it's not going to be too much of an overload after 2 weeks of cosmology and particle physics, looking at massive things to small things. We're going to look at basically scalars and vectors, and we're going to look at how we can use the vectors in practice. But to start with, just going to go back to SI units and dimensional analysis. And so I'm going to refer to the tutorials next week so that you can come back and have a look. Now, it seems a bit obvious, but I do have this IC strategy that you can use, and it follows the textbook. So when you have a problem, you want to identify everything that you need. So I usually write down the variables that you're given, what you're trying to find, and so that's the identify part. To set up the problem, you want to choose the equations. So basically, what equation do you need? Usually for kinematics, you need to find time or the initial velocity, just for an example. And then you want to execute it, so that's where you do your maths. But the important part I want you to do is evaluate your answer at the end. Does it make sense? Is it the distance that you expected, or is it a really small distance and it's not making sense? So that's a sort of evaluation. And then also using dimensional analysis. So I've got that up on all the pages that we have on Canvas, but also I'll keep referring to it as well here. So we don't have too many problems or difficult problems to go through today, but there will be some, and we'll go through. So the first thing is units. Now, we see them everywhere. They're obvious that we know about them, but you may not know where they actually come from. So basically, all measurements must be specified by a relative or relative to some sort of standard. And that's what we've got a picture here. So I've got the units on the outside in the darker colours, and then on the inside is some sort of standard that they've been derived from. So, for example, what's an obvious one? Metres. We have F for M, and so that's using the speed of light, c. So c is referred to the speed of light, and we'll come across that as well. So we have base quantities, and they're defined by a standard. And so all these quantities are defined by base quantities as well, and they're derived. Not sure why my email's going up like that, but that's okay. I'll have to change my PowerPoint setup. So if we have a look at each of these and the units, so the one that we're going to come up against next week when we start to look at Newton's laws is force. So if you think about how we actually calculate force, the most obvious equation, one of the ones that we all know about, is force equals mass times acceleration. So when you think about how that unit would actually look like, or what units we use to get force, we have mass in kilograms, and we have acceleration metres per second per second. So that's the actual unit for force, but we've actually made it a little bit more simple, just write 1 Newton. The reason I'm saying that is because we can actually use the equation to define what the expected unit at the end will be. And so we'll have a look at how we can do that. So we can use dimensional analysis to look at derived equations to make sure we can evaluate the answer and make sure it makes sense. But also we can get the expected unit, for example, for a constant or anything that you're trying to find. Another one is pressure. So that's force over area. So we have force being newtons, which is also equal to kilograms per metre second. Meters per second over the area. And you'll use that when Lachlan comes along and does some thermal physics with you. We've got energy and work, and we'll come across that in week 3 of my lectures, and that's joules, and power as well, just after we look at work. And we've got some electrical ones, which I'll leave for Lachlan to show you. As well as where's mole. There we go, we've got mole as well. So all of these units are defined by these standards here. So it's got to be metres, seconds, ampere, Kelvin, mole, candela or kilogram. So all of them can be written using those base quantities, but sometimes we write them with a little shortened or easier unit, such as newtons. So if we have a look at this, we have our standards, we have our 7 defined constants, which are shown in the inner circle of our picture there. And you can actually see all the information you need to know about measurements and units on this website where they're defined. So we have 1 metre, so 1 length of a path travelled by the speed of light in a vacuum. So that's where that c comes from, that's our standardised constant. And so it comes up as hertz or per second because we have 1 divided by the speed of light. And we can find the length of the path, and that's what defines 1 metre. We've also got 1 second and 1 kilogram. I'm not going to go through all of them, it's just more to give you an example of where they actually come from. But I do have a summarised table here, and they were updated back in 2018 or 2019, I can't remember now. It's about the time I started here. So here's a table that you can find also on that website. So it has the defining constant, which is shown on the inner circle here. And then we've got the symbol here that's represented there as well, the value of each of those, and then the units that we get, and then we can use those to find the base quantities there. And then each of them are defined here using the proposed little definition. So like I said, there's a lot of text there. I'm not going to read it out, but it's something that you can have a look at in your own time. Especially if you're doing some chemistry, or you can have a look at 1 mole as well. And it makes a lot of sense when you start to look at concentrations, molarity, and all those different equations. One more thing before we move on is the scientific prefixes that you will need to know. So you'll probably know most of them quite intuitively because you've used them throughout your lifetime, but there's some that you might not have come across too much. So the ones in red are the ones that you need to know. So that's pretty... all the rest you don't need to remember. But, I mean, if you do come across any of these, you won't come across them in an exam, but if you do come across them, you can easily just Google the unit conversion, or you can remember it. So we've got mega being 10 to the power of 6, so this is starting the large end, or kilo, 10 to the power of 3, so 1,000, all the way down to milli, micro and nano. So nano is the area that I work in. I work in nanotechnology, so I often use this one, and you'll see it. I'm trying to think where you'll see nano. Maybe in electricity when you look at nanoamps and microamps. So it's 0.000001 of a metre for micro, and then add another 3 zeros for nano. So the ones in red are the ones that you need to be able to use and convert quite readily. And we'll look at unit conversions in a moment as well. All the rest, not so much yet. So we're going to look at dimensional analysis. So this is what we can use to examine relationships in terms of those base quantities that we defined with the SI units. So I found this dimensional analysis. The answer is right when the units cancel, so that's what we're going to look at. But then also we've got another way to use it. So we can use it to look at unit conversions as well, or we can use it for derived relationships. So you can use dimensional analysis and determine that the derivation is a lie. And we'll have a look at an example how we can actually use that. So basically it's used to analyse the relationships between those physical quantities by identifying their base quantities. So go back to the metres, seconds, rather than newtons, and then we can look at cancelling them out, just like we do in algebra, and see if it makes sense. All right, so here's the first one. We have our unit conversion here. Now let's see, like I said, I haven't used this room before. Let's hope it's quite smooth. I was hoping this would be big enough, but it's not, so I'm going to put it on and switch it around. And unfortunately, I think the university's firewall doesn't allow me to share my tablet with my computer through the lecture. Is that not working? This is why I restarted it earlier. There we go. Now let's hope it all works smoothly today. So this is the example that we've got on the slide here. So we're just going to do some simple unit conversions just to show how we can use dimensional analysis in our work. So hopefully you can see that okay. That. All right, so the first one there is relatively easy. Make sure everyone can hear me online. So we're going to convert 15 inches into centimetres. And we have another example in the tutorial next week. So you can have a go at that before you attend the class. So the first one is converting 15 inches to centimetres. So the first thing you want to do is you want to identify how many centimetres there are in an inch. So really, really straightforward. We start with the basics. 15, if my writing is any good, which is not. And so we can multiply it. It's about 2.54 centimetres in 1 inch. And so what we can do now is we can have a look at that and go, okay, so we wanted to convert to centimetres from inches. So we got inches on the top and inches on the bottom, so they cancel out. And so I'll try and do this through the problems as well, like in kinematics. So all we're left with is centimetres now on top. So our final units right now have to be in centimetres. See, very straightforward, but it's such a basic and useful technique to be able to do, especially when you start to get into the harder derivations and equations. You'll find it really useful. So, 38.1 centimetres should be that one. We're going to go for a little bit of a long-winded one. So this one is a bit more relevant to what you've done already. So we're going to convert 1 light year into millimetres. So we're going to define what 1 light year is. So 1 light year is equal to the speed of light. You could write the more accurate constant if you like. So we've got 3 times 10 to the 8 metres per second, and that's times 1 year. So we've got that now, so we can now we can start doing a similar equation to what we did, calculation as to what we did previously. So we can write 3.0 times 10 to the 8 metres per second. And what we want to do is convert that to millimetres. So we need to get metres to millimetres. So we have 1,000 millimetres per metre. So I'm going to do my little bracket. And just an FYI, if I have a unit conversion, I just Google 1 light year into millimetres and it'll give it to you. But this is just for the fact that it's useful when you need it in an equation setting. But yeah, just wanted to put that out there too. All right, so we have 1,000 millimetres in 1 metre. So we can actually cancel out metres and we have millimetres left. But we still have seconds, so we need to get rid of that. So we're going to have our 1 year, which we have here, and we're going to convert that into seconds, and that will cancel it out. So we have 365 days in 1 year, and then we're going to move on to the next conversion. So we have 24 hours in every day. So the years are cancelling out. We've got day cancelling out. So now we need to convert the hours to minutes and then seconds. So we have 60 minutes per hour. And we have 60 seconds in every minute. And so you can cancel out the units as you go, or you can completely write it out. So we've got days, hours cancel out, minutes cancel out, and now we have seconds on top and the seconds on the bottom, and the only unit left is millimetres. So once you multiply 3 times 10 to the 8 by 1,000 by 365 by 24 by 60 by 60, you're going to get quite a large number as expected. So that's where the evaluation comes in. If it's really small, then you've done something really wrong. And we get 9.4 times 10 to the 18 millimetres. So we're going to come across this type of thing, for example, in laboratories. So when we do the cosmology lab this week, you're going to have to do a similar... I'll leave that up. It's on the slide as well. So we're going to do a similar conversion where you have... And you can have a look at that before the lab, so you're not doing it in the lab. So I'd advise that you've got laboratory videos for the online content if you can't make it. So this is the same thing, just because my writing's atrocious. I've got it a bit neater here. So you can see how it's converted there. All right, so we've got unit conversions. If we go back, did you want me to leave that up? You'll have access to it. It's on there. But yeah, so we've got to go to the next part of dimensional analysis. So we've looked at checking units, and now we're going to look at deriving relationships, which may be incorrect or may be correct. So what we can do is we can use the dimensional, what are they called, dimensions, and we indicate those in the big brackets there. So for example, time is T, length is L, mass is M. Now it doesn't matter what symbol you use, not really, as long as you're consistent, you know what it is, but these are the ones that I'll be using in the lectures and then in the tutorials as well. So we've got the quantities, like they can be subtracted or added together, but in the same way as dimensions. So we're going to look at how we can use it for equations. So we can use it to calculate quantities, which might change, and it will depend on the situation and the units, but the dimensions will always remain the same. So I've got an example here. So the area being either pi r squared for a circle, or the square could be base times height. The units will be in centimetres cubed, or the length measurement that you've used squared. But yeah, so the dimensions of that will always be L, so being the length dimensions squared. And so you can see that pi obviously doesn't have units, so it doesn't have any dimensions to worry about, but radius will have some sort of length. Similar to base and height, both are length quantities. So we're going to have a look at how we can use it for these two equations after I have a drink. All right, so I've got my two equations here in terms to calculate distance, x. So I've got velocity, time, and acceleration in these equations, and we'll have a look at the kinematics starting in Wednesday's lecture. So we can start writing the dimensions for each of those terms, and then we can put those into the equations, or practically just substitute them in, remove all the unitless parts out of the equations, and then cancel them out to find out what type of unit we have. So we expect for distance that the unit that we'll be left with is just length, nothing else. So let's have a look at how we can do this, as long as this works. All right. Oh, is it gonna, I have to reset it every time. It's a bit slow, this room. All right, so here's our two equations. Now, we're going to go with the first one first. So the first equation has x, so I'm just going to define the dimensions first, just so we don't get confused. T is time, v will have length over t, and a will be similar, but it will be L over t squared. Done that right, haven't I? Yep, okay. So we can start putting those into the equation. So we expect it to equal L. So for this first one, we don't need to worry about the half. We do need to worry about the squared. All right, so velocity, it can go in, L over t, and then we have t squared, and we can do the plus. Don't need to worry about the 2. We can put the dimensions for acceleration in there, and for t as well. All right, so we have our t, 1 cancels out there, so we're left with L over t. And then we can do the same thing here. 1 cancels out here, so we're left with LT. So I think you can see already, and obviously it's the first one, so I'm not going to make the first one the right one, that it's not going to be equal to L, because it doesn't cancel out to give you L. In fact, it gives you LT, and then we've got plus L over T. That's left. So that does not equal that what we expect. So we're going to move on to the next one now. So the next equation was x vt plus a half at squared. And this one, we will come across this equation again. So this one will equal L because I've done it that way. But let's just check. So L over t for velocity, t for time, and then L over t squared for acceleration, and then t squared for t squared for t squared, for time squared. So these cancel out, this cancels out, and these are added together. They don't give you 2, they're just added together to give you 1 L. And so that's how, if you come up with that equation, and you're like, is it right? Should I check? You can do that dimensional analysis to check. Also, you could do that during your equation, like when you're plugging in the values. So you could put in all the values for the equations here, and then you can cancel out the units as you go. And if you get the expected units, you're all good to go, probably, as long as your calculation's right. Okay, so that's dimensional analysis. Looking at the time, should probably get on to vectors. Was there any questions about that at the moment? Like I said, it's stripped back to basics. What I'm doing is I'm giving you that false thing of everything's going to be easy in my section. No, I've started off really easy, and then we're slowly going to get progressively a bit harder through these lectures, but nothing that you can't handle. So we got vectors and scalars. Scalars is one defined number, so that's your magnitude. Vectors have an additional direction. So I'll always define what is a scalar quantity and what is a vector, but if in doubt, you'll see the arrow on top of whatever it is you're looking at. So for example, we'll have these vectors here. So the magnitude of a vector will be written as either the symbol that you're given, for example r, or it'll be written with the parallel lines on the outside. So you can find, we'll have an example where we find the magnitude of a vector, and it will be given by the parallel lines. So we have speed and distance travelled are scalars, and we'll have those definitions more defined in Wednesday's lectures. And then we'll have a look at how we can, at different versions, for example, displacement is a vector, so distance is not. Displacement is a vector, and it's written by r, x or y, or whatever coordinate you have. So delta is the change in something, so I'll define that now. It's used a lot in equations in general, so it's just written as the final value of whatever it is you're looking at minus the initial value. So the change in this vector r is equal to r2 minus r1. So you might have two vectors with x, y and z coordinates, and you can find the change in those two vectors quite easily, and that will give you the final displacement. For velocity, we can find velocity by using the derivative of r. So we can find r as a function of time. We can divide it by the time that we have, and we can find the change in time, I should say. And we can put in perhaps we found our change in r value. We can put this into our velocity equation, and we can get the velocity vector. So for this one, you can actually put the vector equation straight into that, and you can find the derivative of that to find the velocity. And again, you can use the velocity vector that we have and plug it into the acceleration. Really, really simple. So we're not going to do much more to that today, but it is an intro into to Wednesday's lecture. So we need to add, subtract, multiply. We need to be able to do all those things to our vectors because we'll be using them a lot. So first in kinematics, then in Newton's laws stuff that we're going to do next week, and then starting to look at rotational motion. It'll be integrated throughout, and even in the electricity part. So first things first, we're going to draw vectors just to bring it back. If you're unsure how to do it, there's just an arrow. So the size of the arrow gives you the magnitude, and then obviously we have the pointing in the direction that it occurs. So we have this first vector for A. It's going in the upwards direction, slightly in the positive x if I have my x coordinates going across the room here. And we might have another vector that has the same length and the same direction, so they have equal vectors. They're equal. So they're both equal to A. We can change the direction, and we can get a new vector. It will have the same magnitude but opposite in direction. Really, really simple. So then if we have two vectors, we can add them together. And there's three different ways that I'll show you. The most common one is just by having the first vector at the top end of that one, add the next vector, and you draw the connecting blue vector to give you the sum of those two. Alternatively, you could draw basically the mirror image of that, I guess, sort of. No, not really. But anyway, it will be the other side of the parallelogram. God, it's hard to say with a blocked nose. But yeah, so we got the blue, we got the red. All right, we'll get this right. We've got the B vector going on the bottom, and then we have the A vector going from the top of the B vector, and you can draw the blue. And you can see that it's the same vector at the end, the blue one. And then obviously you could do sort of a picture of those two vectors connected together and draw a parallelogram. So all these ways to draw it. Most of the time you use trigonometry anyway, but it's important to have that visual as well on how the new vector is going to look. So that way you can predict what direction and what magnitude it will have. So we have the parallelogram. So the first example was using A and then B connected. The second one was using B, then A connected. And this one's just drawing two dotted lines towards the new vector. And that will give you the sum of those. If you have two vectors in the same direction, the only thing that will change is the magnitude. The direction will remain the same. If you had one in the opposite direction, obviously the magnitude will change as well, but it might decrease. So for example, we have two going in the x direction as an example. It will give you a higher number in the x direction. For this one, we might have A, and we might have one going in the opposite direction, and it's going to decrease slightly, as expected. When you have more than two, this is going to just be an extension from adding two vectors together. You could either do it sequentially, so adding A and B, and then finding that new vector, then adding C to that one, or you can combine them all, A, B, and then C, and then draw the new R vector. So you just pick the way that resonates with you, what makes it easier for you to do or faster. So for this one, we have A and B to form the new D vector, and then we've added the sum of A and B, D, with C, and it gives you R, or you could just A, B, C, and then draw the R across and find that one. I think that's all I've got for that one. Okay, so if we have, we can also find the A, B, and C in the other order as well. But I don't know. I don't usually use that method. I use the previous method. And we'll also see towards the end of this lecture, or is it tomorrow's, we're going to look at the unit vectors as well. So we'll actually define I, J, and K hats, and they'll also be another strategy to solve the vectors. All right, so if we have the opposite where we're subtracting, it's going to be very similar. So subtracting B from A, for example, is going to be equivalent to adding minus B, so reversing that direction to A. So you can. So these are the types of relationships you should remember, because they'll come up again in practice. And so we have A plus minus B is equal to A minus B, and we've drawn it out here so you can see that the sum of that vector here is equal to, is the same on both sides of that equation. So we're going to start looking at other like multiplication of vectors in a moment too, but also, there's an obvious way to do it, and that's drawing it out and finding the trigonometry, magnitude and direction of the vector. So if we have this right angle, we might have a vector going up and a vector going across, and we can find the new one if we know the angle. And so we can find the direction as well as the magnitude just using simple maths. You don't even now have to draw it out if you don't want to. So for this example, we have a cross-country skier, and it ends up 2.24 kilometres from their starting point, in a direction of 63.4 degrees east of north. So we can calculate the magnitude using the hypotenuse, the square root of 1 squared plus 2 squared, and it will give you the magnitude. And then you can find the tan theta opposite over adjacent to find the angle of that one. And so that would give you about 63.4. So I was going to go through that, but I'm a bit slow in today's lecture, so we'll leave it there. But it's pretty, and we'll come across this type of method a lot, especially when we start to look at the initial velocities of a projectile, which has both x and y components, and we'll have to split that initial velocity out using a similar method to this. And also force. And this which goes quite nicely into components of vectors. So like I said, projectile motions will have a movement of a ball going up and across, so both x and y directions. We don't do too much in a third dimension, in the Z direction, in the first few weeks, but we will cover a little bit in the talk section. Excuse me. All right, so this is our ball, A, travelling with with initial velocity of A, so it has its direction going up. We can separate that out into the Y and X directions, and that's because it's really hard to solve a problem without doing that. Projectile motion with X and Y coordinates without separating it out. And we'll have a look at how we can actually do that in the third lecture this week. So we could separate our initial velocity, so whatever velocity it's been the ball's been kicked at, into the Y and X, and then solve for the projectile motion. Usually the way that projectile motion problems are done is finding the initial velocity, then finding time, and then solving for whatever it is that you need. And I've got another example that we'll see for next week's lectures when we start to look at banked curves and the force or free body diagram of the banked curves or the object on the banked curve, and we'll see that next week. So we'll come back to that. So calculating using the components, we can see here, so we can use the components of a vector and we can find both the magnitude and direction. So we've got this R vector and it's the sum of A and B. So we can find we can separate each vector into the X and the Y, and then we can just add the magnitudes together. That's usually the two strategies that you can use. You can either put the vectors into the R or displacement equations without separating out the X and Y, or you can separate out the X and Y and then do two separate equations for the kinematics, so the X derivative or the Y. And it will make more sense if it's a bit confusing now. It will definitely make sense in Wednesday's lecture. So so we can either do it all at once to find R, or we can separate R into X and the Y. And this is where we start to introduce the I, J, and K hat. So these are the unit vectors. So the I hat represents the value in the X direction, J points in the Y, and the Z is the K hat. So like I mentioned, most of the examples, the applied problems that we'll see, will not have the K in the Z direction, but we will visit that in the last week. And it's usually written like A arrow, so the vector. We have the magnitude, I hat plus the Y, J hat plus the Z, K hat. And if it doesn't have any value, you just don't write it. Because that often gets confusing, especially when you start looking at the cross products, which we'll see at the last bit of this lecture. So we're going to look at how we can multiply vectors. So we've got three different ways. We can first multiply a vector by a scalar product. And with this, it's pretty simple. So we have our scalar product being C, for example. So the product of C times your vector will have a magnitude increase based on that scalar value. So if we have a scalar value of 2, it's going to be twice as long. So a very simple way to calculate it. So if we have a unit vector of 1 I hat and then maybe 2 j hat, we can multiply it by some sort of value, for example 3. So it'll be 3 I hat plus 6 j hat. Simple maths, just multiplying the scalar product by each of the unit vectors that you have. And it's the same with direction, so it could change the direction of those, but it's based on the sign. So that's the most easiest one. So this will be the first vector problem in next week's tutorial. And then the part B for that question is going to be the dot product. So it's either called the scalar product or the dot product. Some people even call it the scalar dot product. But there's two ways to solve this, and we'll have it in the projectile motion laboratory next week, where we'll actually draw that out and it will actually prove this maths as well. So if you have two vectors, A and B, with an angle separation of theta, you can find the scalar product or the dot product using this equation AB cos theta, where A and B are the magnitude of those two vectors, and then you've got the theta angle here. And so we've written it here, so the two lines, the magnitude of A times the magnitude of B. and it will get by the cos angle that you have, and that will give you the scalar product of the two vectors that you have. The other way, which you'll see, is you can draw your A and your B, and you can draw a line that is 90 degrees to vector A. And this will give you B cos theta, and you can actually find the A dot product, which is represented by this little dot between the two vectors, as A times B cos theta. And the reverse way is like so. So we do the same thing, a right angle to the two vectors. But usually it's easier to do it so it crosses the largest vector, just because it's easier. So like I said, we'll do that in next week's projectile motion lab in the introduction part. So that's the scalar product. And the other way is if you have two vectors with the different components, you can simply multiply the magnitude of the I values, the j values, and the k values. So if you have one I hat for the A vector, two j hat for the next one, you can just multiply it by the equivalent values for the B vector, if that makes sense. So I might just quickly write an example. Sorry. So if you have two vectors, A and B, you might have 1, 1, and 1 with the I, j, and k, and then maybe for B you'll have 2, 2, and 2. So it would be 1 times 2 plus 1 times 2 plus 1 times 2. You add them together and you'll have a new value. And it will only be a value, it will not have anything else. And so that's the second part of the next week's tutorial, where we will look at how we can find the dot product. But the one that gets people a little bit more confused is the vector product. But I'm hopefully going to make it really simple. There'll be two ways you can solve it. So this one you can use the right-hand rule, and it's represented by a cross. And that cross is really useful if you're a visual person like me. This is where you have two vectors, A and B, and you need to find the third vector using the right-hand rule. So we'll see examples where we can apply that, especially in next week's laboratory and in the tutorial next week. For example, torque is when you grab a wrench and you rotate it, you have a third direction vector that goes through the rotational axes. So in the last few weeks of this course, we'll start to look at how we can apply this type of vector cross product. All right, so we get the magnitude of the vector cross product, which will have a new direction, unlike the scalar dot product. And we can multiply the two magnitudes of A and B times sine theta. And what you'll notice is that you're going to get a completely new direction. So if you only have I hats and j hats, or x and y components, the new direction will always only have a z direction. And so that's good when you evaluate your answer. So if you have values in the x and y direction after doing a cross product with only x and y, then you've probably done it wrong. But we've got an example. I use this equation here. So what I do is I have my two vectors, A and B. I have the values for the I, j, and k hat, or the x, y, and z respectively. So I write my values in here. So it could be 1, 1, 1, or 2, 2, and 2. And then I'll use this equation and just substitute the values in. So I have a cross. This is where the visual element comes in, and we'll do the cross. So we have AY times BZ. So you just multiply those two values. And then we have BY times AZ. So that's the first part of that equation. And the next thing to remember is plus, minus, plus. So you'll see here, this will give you a new value for your x component. So whatever this is your new x component value, but you'll notice that it only uses the y and the z directions. You've got the next one, which is to find the new y component, and this one will not use that column. It will go ax to bz, bx to az. And then to find the new z component, it's going to be ax, by, bx to ay. And then it's just remembering that it's minus in the brackets and then plus, minus, plus outside. So yeah, that's how I visually remember that equation, so I don't have to look it up. And I've got an example here. So we've got 5 minutes, so we'll go through this one. And then I'll get you to open up the Canvas quiz if you want to, and we can go through that. So, nothing is worse than having kids with germs in your household, eh? All right, let's just wait for this machine to warm up. So I'm going to have my two vectors. I've got A and B. I've got the picture here as well. All right. And if you're happy with this, you can move on to the quiz if you like and test your knowledge to make sure. But we'll go through this. All right, so based on my equation that I had on that previous slide, I'm going to draw my little matrix. So the first vector is 6i hat, so that's my x. It has no y and it has no z. So my b vector is 4 cos 30 degrees I hat plus 4 sine 30 j hat. Now you can calculate the values or you can just plug them in like that and calculate it at the end. So I've got my matrices, so A on the top, B on the bottom, and the X, Y, and Z components here. So for the first one, I've only got an I value for the I hat, 6i. So the other two are 0. So this is where you can see that we're going to get a different direction, right? Because I said that if we only have directions in the I and J, or the X and Y respectively, the new direction will only be K. So for this scalar product, I'm already expecting that we're only going to have a Z direction for the final product. All right, so we can do the same thing. So we got 4 cos 30, and I'm going to do an arrow because I didn't make room, and 4 sine 30, and then it's 0. So the first one, what did I say the equation was? So it's going to be plus, brackets, minus, brackets, plus, and each of these have a minus inside. And so the first one's going to be across from the A to the B, so it's going to be 0, and then 4 sine 30 times 0. So that's already going to be pretty simplified. The next one's going to be the, so this is for the new I value, J value, and K. So this one's not going to include the middle column that we're trying to find. So it's going to be 6 times 0, 4 cos 30 times 0 off to this column here. And then I'm just going to get rid of those arrows. Actually, I can't. All right, so this one's going to be 0 as well, just like I said. So the final column here for the K, or the Z direction, sorry, I've gone off the screen. All right, so this one's going to not include the K column, but it's going to have 6 times 4 sine 30. And then we're going to have the 4 cos 30 times 0. So our final value for this one is going to just be equal to 6 times 4 sine 30, and it's only going to have the K direction. Now, it's not always going to be that simple. You could have values for each of those, but that's how you solve it very quickly with a simple example. Is that all right? Straightforward? If you have an easier way, stick with it, but I just find that sometimes people prefer that method. All right. So that's the last slide with a summary of those. You can come up back to that for next week's tutorial if you like. But other than that, we've got the questions on Canvas, and we've got 1 minute of this lecture, so feel free to either have a go now or have a go later. That's fine. I will check to make sure there was any questions that were confusing, and then I'll revisit that before I start the next lecture. But other than that, I want to make sure there's time for people to come down and have a chat. But yeah, thanks for enduring my bad cold. But yeah, and I'll see you on Wednesday at 9. Thank you.
zero.